Okay, so you missed the first part, but it'll be recording. It's going to be huge, so you'll have to network and download it. All right, so let's see. What else did I want to ask you? All right. What if f were 0? What would happen? Right? You have a first order system with just a constant. Okay, it won't oscillate, right? Here's your transient. Holy cow, what the heck is that? Doesn't that look like there's an omega in there? What in the world? Well, it turns out if you simplify it, you get this. Where's your steady state? 2? Okay. So look at this. Now, look at the equation, and what I'd like you to do is be able to say, oh, I know what the steady state value is. Right? How would you know? Well, if you assume it's stable, okay, if it's stable, this guy right here will finish changing. He won't change anymore at steady state. So he'll be gone, and the f's are gone. So what would x be at steady state? 2. See how you can sometimes, if it's easy and you can look at the equation, hey, look at the equation, give me the answer 2. That's what I'm looking for, right? Now you have a little trouble maybe because you turn that in on a test and I'll say, I think you copied this. Where did it come from? You say it came from my head. Yeah, you're right. You get the idea? But you can look at the equation and if they're not too hard, you can do it. You can do it in your head, right? What if you can't do it in your head? How would you find the steady state value if you couldn't just look at the equation? Or maybe I hid the equation, didn't give you the equation. How would you find it? The 4 steps, you remember the 4 steps? Okay. It only records what shows up on the computer, so it's not going to record this. Right? But put this in your notes. Remember, if you want steady state solution for a constant, what do? You get a transfer function. That was step 1, right? Can you get a transfer function for this for me? Here's the equation. Can you get a transfer function for me? How do you get it? Yeah, you're going to take the Laplace transform. That's the official thing, right? But what we're going to do is everywhere you have a derivative, you're going to put s. What if you had 2 derivatives? S squared. 3? S cubed, right? What are you going to do about the initial conditions? You ignore them. Mathematicians freak out, but hey, you ignore them because they disappear. Okay, so anyway, let's see, x, 10, x, okay, so it's going to look like this. It's going to be s, x, and I'll put a little bar over it, meaning I took the Laplace, plus 10x, right? Equals the input. I'll just call it I for input. How's that? Can't see it? There's always one in the front. How's that? That? Okay. All right, so now what's the transfer function? Always output divided by input. And should you take 30 minutes to get these transfer functions? No, you should be able to take 3 seconds to get these transfer functions. That you always do it the same way. And you ask me a question later, I got your answer. Okay. X over I equals what?
S plus 10.
It'll be the input 1 divided by s plus 10 in the denominator. See that? So this stuff here goes to the denominator. Okay? What's the power of the exponent in the solution? You saw it. I had it up here on the Mathematica. Remember what it was? E to the what? Negative 10. How do you find it from a transfer function? Remember? Take the denominator, set it to 0. Solve for what? S. S equals what? S equals negative 10. That was the power of the exponent. It always is. Okay? So instead of solving the differential equation, if I were to say, what's the power of the exponent? Boom, get a transfer function. Boom, solve for s's. Bang, bang, bang. If you got 6 of them, you got 6 e's. Okay? Good? How do you know it's stable? You saw it was. How would you know if this is what you saw? How would you know it's stable? Negative, because you're going to get e to the negative 10t. Negative 10 times t, that e is going to disappear. How would you know it was unstable? It'd be a positive. How would you know it was marginally stable? This would be a 0. E to the 0t is 1. Doesn't get bigger, it doesn't get smaller. It just kind of hangs out. Got it? So that's marginally stable. This would be stable. Does it want to oscillate? No, you saw it didn't. Does it want to oscillate? How do you know that? By looking at this. They're not complex. They're not complex. If these guys are complex, then it'll want to oscillate. Doesn't mean it will, but it'll want to. So far, okay? Is it obvious to you that there's no way you can get a first order system to oscillate? Should be, because you've got to get a quadratic in order to get square root of something. Square root of a negative number is the only way you're going to get a complex number. So if you don't have at least a square, you ain't going to get anything to oscillate on its own. Make sense? Okay. Let's get back to finding that steady state value for a constant input. How do you do it? Step one. You solve for what you want. I want x, I'm going to solve for x. So here we go, x equals the input divided by s plus 10. Step two, what do I do? Well, that's step three, but I'm glad you remembered. You replace the input with the Laplace of the input. And how many inputs, when I ask you to do this, how many inputs are you going to have in this class? Two. I'm going to hold you responsible for two. And what are they going to be? Constant and a ramp. And I'll tell you what a ramp would be good for in a little bit. Now, you go out and you work for the Navy. They're going to do sonar. Bing, and they send out these ping, ping, pings, right? They want to make sure that if they ping somebody, that person or that thing or whatever, the enemy, doesn't ping you back and they go, oh, well, okay, I heard it. Right? So what they'll do is they will output some sort of weird sound. I mean, weird sound. And they want to know, what should I receive back? Well, they need the Laplace transform of their input. Is it a constant? No. Is it a ramp? No. It's some weird, crazy thing. And how do you do that? You go to Mathematica and you say, give me the Laplace transform of blah, 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 and you type it in, and then you use the procedure, or you go to a table of Laplace transforms. So the input can be very complicated, and the method works. I'm going to hold you responsible for two of them, okay? And figure that if you do this work, and if you do this work, you'll do complicated ones, and hopefully you'll learn it. But everybody's going to have to be able to do two. Okay, what's the Laplace transform of a constant?
S.
It's 1 over s times the magnitude. What was the magnitude? Do you remember?
The constant.
Yeah, what was the constant? You remember? It was 20. It was 20, wasn't it? Yeah. So this would be, the Laplace of this guy would be 20 over s divided by s plus 10. Now, what's step 3? Multiply by s. Don't ask me why, it's a theory. Okay, multiply by s. Step 4, take the limit as s goes to 0. So that guy and that guy cancel off. S goes to 0, you got 20 over 10. What's the answer? Is that what Mathematica told me? Yeah. Okay, so if you have one and you can't spot it, that's a technique to find constants or ramps. Okay, so why do you have constants? Okay, suppose you have, let's do something violent since, the U.S. is bombing everybody. Okay, so let's say you want to launch a missile and you want to hit a stationary object. Okay? Then what you want to do is you want to have an input that says, you want your missile to land at a known at a constant value. Of course, it's 3D. I understand that. We're only doing one, but it's basically a constant that you want to hit. So what you're looking for is what's the steady state error, or what's the steady state location. So if you got a bunker 10 feet from you, you don't want to land the missile at 9 feet. Well, maybe you do. Maybe it's a big missile, right? But you want to land it at 10. Dead nuts on, correct? So you would use an input of a constant. Suppose you're it's a truck and it's moving at a constant speed. Now what do you want to do?
Linear.
Yeah, the position is changing as a linear function of time, right? So now what you want is an input that's a straight line. The slope would be the speed that the vehicle or whatever is hitting. So then you launch it, kaboom, right on the money. What do you think you would do with a parabola? Constant acceleration. right? So, you know, you're shooting an airplane, the airplane goes, holy cow, and he hits the gas and off he goes, right? You want to hit him anyway. So you would want your system to have a good steady state value when you have a parabola. Okay? What are you zigzagging? What's your input, right? So anyway, you get the idea of what these inputs, different inputs are for. If you want something, you know, safe, you have a robot. If you have a robot and it's going to come over here and pick something up and then move it over here and set it down, you want constant inputs. Because what you want to do is get the hand over the coffee cup, not 2 inches beyond the coffee cup, at the coffee cup, pick it up. Suppose you had the coffee cup on a conveyor belt. That would be a ramp. So what you do is you tell your robot, I want you to do a ramp input, and I want the steady state value to be equal to where the cup is. Right? No violence there. Got it? So you get kind of the idea of what the inputs are for? Okay. I'm not going to ask you what they're for. I'm going to say, I want the steady state value. I'm just seeing if you can do the math. Would I do the math for something like this? No, it's too easy. But on the exam, I'm expecting you to show me you can do the math because I'm trying to get you ready to do the hard ones. Okay? So that's what it's for. Okay, so you can do the steady state, right? All right, let's pull up the Mathematica and let me keep asking you questions. Okay, so if you drop out the F, then you only have the constant, and we've just seen that the steady state value is 2. So what will happen is if you push on it with 20, it's going to go to 2. All right. And now what I want to do is I just want to focus on that sinusoid. So just to keep it simple, I'm going to use 0 initial conditions. So I put it in here, and if you're curious, this is how you put in an initial condition. You say x at time 0 is 0. So there's my 0 initial condition. I ask it to solve for x and time, and here it is. Okay? So let's take a look at that. That would be the solution when you have 0 initial conditions. Notice the C1 is already factored in. It's a little harder to see where the transient is when you do it this way. It's much easier when you have that C, because you can spot it right away. Notice that not everything disappears because you see the e to the minus t here, and there's the e to the 10t here. So when you multiply it through, this stuff over there stays, this stuff over here disappears. It looks weird, but, right? Hey, I didn't write Mathematica. I just use it. Okay, so what I would like is I would like to see what this does for various frequencies. Now, I'm going to do the plot. I'm going to say solve it, solve it, solve it, solve it. But before we do, I just want to ask you, what do you think is going to happen? Let's say, for example, this frequency right here, omega, I write W, this frequency that I'm forcing it with, suppose it's really, really slow. Real slow. So the sine wave is maybe over a day. I mean, it's going slow. What do you think is going to happen? What would the response of the system be? It would be slow, and it would probably just kind of follow with the factor of 20, you know, with the factor of 2. What it's going to do is it's just going to kind of follow it with the same amplitude. Does that make sense? What would happen if you sped that up and you started going really fast with this omega? What would happen now? It would respond at the same frequency. We'll see that. It will always go at the same frequency I shake it. It will always do that. But will it be big from peak to peak, or will it tend to shorten down? Why will it shorten down? Very good. The time constant. See, what will happen is the sine wave comes on and says, hey, come on, let's go. We're going to come up here. And he says, okay, I'm with you. Sure, I got this time constant, and I'm coming along. Coming along, right? But before he can get there, all of a sudden the sine wave is down here because he's going faster than the time constant, right? So all of a sudden the sine wave is down on the negative side, saying, hey, come on down this way now. Oh, okay. You got friends like that? Yeah, okay, here I come. Right, but they have a time constant. It takes them a while before they can begin to respond. And before they get down there, you're up here again. You see? So what's going to happen to the output? If you're going from, say, 1 to 1, what's the output going to do? At low frequency, he's going to tend to want to be up there with you and be down there with you because you're going slow enough that his time constant will allow him to keep up with you. Right? Make sense? But if you're going too quickly, what will happen is by the time he heads up there, you're down here and now it begins to come down. And now you're up here and it tends to go up. So the peak to peak of your output is not going to be anywhere close to the peak to peak of your input. You see that? But you will always find that when you peak, he'll peak. And then when you trough, he'll trough. Or sometime afterwards, right? Because he's not completely with you. So his amplitude is going to be shrunk and he'll be off in phase, right? When you peak out and start coming down, he hasn't quite decided to come down yet. And now he decides to come down. So he'll lag behind you usually. Does that make sense? Okay. So that's the kind of skill that I think as an engineer you need to be able to say, look, I've heard about time constants, I know about frequencies, I know about these things, and here's what I think it's going to do. When you hit that on button, the thing's going to blow up. Oh, well, that's not a good design. Unless you're making bombs, right? Oh, that's not a good design. Well, maybe you're wrong, right? So then you put it into either Mathematica or Simulink or MATLAB or something and say, sure enough, I was right. But when you're designing things, you want to be able to think of solutions. How can I make this work? And for that, you need to be able to say very quickly, it will or it will not, or this is my prediction. This is what I think it's going to do. Rule that out. Rule that out. Get the idea? So hopefully you'll be designers. Okay, let me prove to you that it kind of does that. Okay, so here we'll plot this output, the answer. I'm not sure I executed it, so let me execute it all. I'll post this Mathematica file if you want to play around with it too. So all I did here was I just said simplify. This percent sign means the previous thing, the last thing that you did. So it says simplify the last thing that you did. Okay, so here we are. We're going to make it an initial condition of 0. Bang. Okay, so now it has that. Now I'm going to plot it for various frequencies. So here we go. Give me a frequency that you want. Okay, how about 1? We'll see what happens and we'll plot it. Okay. On an exam, I might ask you, where is the transient? Is this the transient over here? Is this the transient over here? Yeah, usually the transients begin at the beginning. You notice that this doesn't at all look sinusoidal. No, because it's going through the transient piece. Right? It's going through that transient. Now all of a sudden it begins to oscillate. See that? So if you give it a little more time, so I'm going to just extend the time out there. Instead of 5 seconds, we'll plot it for 10 seconds. Okay, now you definitely can see the sine wave, right? See that? All right, the peak to peak on the sine wave. Notice that that's about a 2.1. It goes down to about a 1.9. So peak to peak it'd be 0.2. Is that about right? Okay. Now, if we speed it up, what do you think it's going to do? From 0.2, will it get to, say, bigger or smaller? Smaller, right? Because of the time constant, because now it's going too fast, right? So let's increase that. So now we'll have an omega of, oh, let's say, make sure that we can definitely see it. We'll do 10. There we go. What's the peak to peak now? Looks like about 207 maybe? 2.07 perhaps, down to 1.9. I don't know, but it did get small? It did, didn't it? Okay. Notice the frequency here. It's 10 times what it was before. Okay, it's hard to see, but if you took a ruler and measured across there, you'd have 10 humps. It's humping at the same rate that this guy's humping at. Okay? Does that make sense? All right. Let me show you, let's see, let me plot the input. The input is f sine omega t, so f is 1. So let me plot, we'll say f is 1, so 1 sine of w t. Let's see, what's w? W is 10. 10 times t. And that. I shouldn't do this on the fly, but there we go. There we go. Okay, so this red is the input. Notice that every time there's a hump, let's count them. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I'm basically saying, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. See? It's keeping up with me. See that? So he's doing the same frequency I'm doing. Make sense? Right? One thing it might be a little hard to see here, but let me see if I can find something with straight edge. Let me borrow your sheet of paper there. Just hold it. You don't have to rip it out. But if you notice, I'm trying to draw a vertical line up here. There's the peak on this guy. Look up here. He doesn't hit at the peak. See that? He's behind a little bit. Because what's happening is because he has a time constant, when the input starts to go up and peak out, he hasn't gotten there yet. So you're on the way down by the time he says, oh, okay, fine, I'm with you now. And he comes over with a peak. See what happens? That's called the phase shift. Okay? So what I'm going to ask you on a test is, give me the magnitude, this thing, and give me the phase shift. Now you could solve the differential equation, get out a ruler, and you could measure it, because that's what's happening here. Or you can use the transfer function. You ready? All right. Let's use the transfer function to find out the magnitude of this. You understand what I'm asking you to do, right? This is for the transient when it's oscillatory. Okay? Not a constant, not a ramp, but an oscillation. And then after you know how to do it, I'll show you why you might want to.
Okay, so we're using the transfer function for the magnitude, or for the
We're going to do it for everything. Okay, so here's my transfer function, right? Okay, so what I want is I want to find the magnitude. Here's what you do. It's a sine wave, right? I'm looking for the magnitude when I have a sine wave. So what I do is everywhere in your transfer function, everywhere you have an S, you put in I, the imaginary number, times omega. Okay? So in the numerator, you got any S's up there? Now I know this is black magic. I know it's black magic. There's theory behind it. You don't want the theory. I don't like the theory. I forgot the theory. But it works. Okay? 1 divided by, okay, you got any S's in the denominator? Okay. Right there. So you say imaginary number omega. This is the forcing omega. Let me put a little F underneath. That is your input forcing omega. Whatever frequency that is, that's what goes in there. All right? Plus 10. Is there any S in the 10? All right. Now you find the magnitude of these. Here's how you do it. Okay? Take careful notes. I'm not sure this is in your book. Okay? What you do is every single term in here, what I'm going to do is draw a picture. And I'm going to draw a picture on a real and imaginary axis. The real always goes horizontal and imaginary up. You don't have to, but this is the way everybody else is going to do it. So when you look at, or if you turn something into your boss and you have it backwards, they're going to go, what? Where did you learn this? You know, cut it out. So anyway, we draw real that way, imaginary that way, just because that's the way we do it. Okay? And then what we do is we come in here and we draw a picture of this. How much real part you have on this and how much imaginary do you have?
all real.
All real? Okay, I'm going to draw a picture. I'm going to say this is a vector and it goes like this. I'm going to offset it a little bit. There it is, and it's the length of 1. The magnitude of him is 1. His magnitude is 1. Got it? How long is that vector? 1. Okay. Then I'm going to draw a picture of this guy. How much real part does he have? A 10, right? Did you say negative? This term right here. That looks like a 10 to me. That's how much real part he's got. This guy right here, this is the imaginary part. There's a number with an imaginary number. Got it? Okay. So I'm going to draw a picture of this guy. He's going to be 10. He's going to be whoa, way out here. Okay, it's not the scale. What's his vertical? Whatever omega is, isn't it? So he's going to look like this. Let me draw him a little closer to the axis. Here we go. way out there. He's 10, and he goes up this way, omega. So he has a horizontal piece and a vertical piece. There he is right there. What is the magnitude of this guy right here? 1. And then if there's another term up there, I say times, 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 times. And then what I do is I divide all of the terms in the denominator. So I say divided by, how big is this term here? Excuse me. How big is this term here? Is it omega plus 10? Very good. This is a vector. How long is the hypotenuse? 10 squared plus omega squared square root. Isn't it? Yeah. So this guy is square root of 10 squared plus omega f squared. Give me an omega. 2. Okay. So if omega f is 2, this would be 1 divided by the square root of 10 squared plus 2 squared is 4. So the square root, 1 divided by the square root of 104. Let's see if Mathematica agrees with us. Oh, I guess I better show you now. It is Monday. Okay. So here we go. I solved the differential equation. Here's the steady state. I take the steady state, and all I did was I cut out this right here, highlighted it, copy, pasted it here, and said that's my steady state answer. Okay. So I'm looking for the steady state. It's got an f in it, so I want to tell Mathematica that, use f equal 1, and then I'm going to plot it. Okay, and what omega did we use? 2? Okay, we'll have to move this, come on. We'll make this say 20, so we see. There we go. So the amplitude is from 0.1 to 0.1. Okay, using chapter 6, here's what we're doing, and I'm getting the magnitude, and it says that it is 1 over square root of 10 times square root of 2. Is that the same thing? It is? Yeah, I think it is. Okay, so they're saying it's the same thing, right? So up here, what is the, let me get a number. Okay, put in omega equal 10, give it to me as a decimal. Whoops. Okay, let me execute. Oh no, it was 2. I'm sorry. Omega was 2. 0.098. Is that about what we're getting? 0.098 on the graph? Come on, plot. Well, this is peak to peak. What's the amplitude? About 0.1, but if you notice this, it doesn't quite come up to 0.1. Not quite to 0.1, and that's pretty much what I'm getting down here. 0.098. Pretty close to 0.1, right? So I want you to trust me. It's the same. It's the same thing. And if you don't believe it, okay, let's change it. Give me another number. Let's say omega is 20. And we'll plot it. There we go. See that one? Okay, so it looks like from peak to peak it's twice, but from here to here it's pretty close to 0.0, let's see, 4? I think it's a little more than 0.4. I think it's like 0.5 or something. Right? Because the tick mark for 0.4 is right there. Okay, so let's do that. Now S is omega is 20.04. It's a little more than 0.04. Is that what you see up there? Will you believe me now? Okay, good. So what will happen is now what I want to ask you is what will happen to the magnitudes as the frequency gets larger and larger and larger and larger and larger? What will happen to the magnitude? Smaller and smaller and smaller and smaller. Okay? So what will happen then is I've just done a plot right here for this is the magnitude on the vertical, and this is the frequency along here. And sure enough, as the frequency goes up, it gets smaller and smaller and smaller. Right? Why? Because it's getting faster and faster from the time constant. So it's going so quickly, the time constant says, man, I don't know what you're doing, but I can't do that. But there will be a little bitty ripple. It never goes quite to zero, but it will have it'll get smaller and smaller. You had a question?
Yes, I just didn't understand why you're dividing the magnitude by, or 1 divided by
Period.
magnitude.
You do it. What happens here, when you're doing the transfer function, everything on the top is multiply, 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 multiply. They only had one, so, you know. And then on the bottom it's divide, 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 divide. That's just the way it is.
So is it necessary to draw one vector?
Well, the magnitude is 1, so, I mean, what if it was a complex number there? Then you'd want to draw a picture, right? In other words, suppose your transfer function looked like this. S plus 1 over S squared plus 3. Then the numerator's not 1, right? So there you better draw a picture. Okay? Now, when I do this, do I draw a picture of this? No. But I've been doing it for 30 years. So if you say, oh, man, that's easy, then don't draw the picture. I don't care. What I care about is this. Get to this. This is where you want to be. And get there as quickly as possible. I have found that when you're just learning, it's easier if you draw the picture, 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 and then write it off the picture. Because you get confused. But do you have to? No. Just like this one. Did I have to? No, because it's pretty obvious. And what's the size of it? He's a 1. Right? What if this was a 2? Well, then I draw a picture of a 2. And I say, how big is the 2? It's a 2. Right? And you say, well, I don't need to draw it. Hey, good for you. Right? Good for you. It's a tool to try to help me make you understand.
What are we solving for here? 1 over square root?
What are we solving for? Magnitude of the sinusoid.
It's not the amplitude, it's the...
Well, okay, call it, depends on what book you read. It's the amplitude, it's the magnitude, it's the...
You're solving for the peak.
The peak. Yeah, not peak to peak, but the middle to peak. If you measure these things experimentally, people will measure peak to peak because it's very difficult to find the middle of something. But it's easy to find peak to peak because if it's something like this, it's easy to lay a straight edge along there and a straight edge along there and measure between them. It's much more difficult to find the middle. So when they measure it, they'll say peak to peak, and then they divide by 2. Okay? So they'll say peak to peak. When you're doing the calculations, it gives you from middle to top. Okay?
So on the test, you'll ask us for the magnitude of the amplitude.
Right, and I'm bad at, sometimes I don't use the same word for everything. Okay? And my excuse is I'm just trying to teach you to, but it'll be magnitude, it'll be amplitude. If you get confused with a word, you say, what? And I'll go, oh, I'm sorry, I meant magnitude. Okay, so if there's some word that I have never used in class, feel free to raise your hand and say, what the heck is this word? And I'll say, I've been talking about time constants since day 1. I'm not going to tell you, right? Or I'll say, oops, I'm sorry, that's also called blah, blah, blah. You know, because it's not fair, right? Because there's terminology and they're all over the place. And the problem is I've learned them, and if I feel good, I use magnitude, and if I don't feel so good, it's amplitude. I don't know. But I use them kind of interchangeably, okay? But it's the same thing. All right. You ready to do? Yeah.
So if you're asking for phase shift, we have to find
I haven't done phase shift yet, but I'm going to. This is the amplitude, or the magnitude, or the size, right? Now we want to know how far phase shift, or the I'm sure there's 3 other words for it. Okay? I want to know the angle between them. Okay? The angle, so that once it peaks, when will the other one peak? All right, so let's find it out. Where do you think we start? Begins with a T. Transfer function. That's where you start everything in this class. Yeah. Yeah, well, you know what you're shaking it with. You always have to know what you're putting in, right? And then you say, okay, well, I'm shaking it with 100 hertz. Okay, that's, now convert to units. You want everything in radians per second. Okay, I'm not big on units, but you know, if you did your unit conversions, it's radians per second is what you always need it to be. Okay, can you all convert from cycles per second to radians per second? Okay, good. I may put that on the test just to make sure you're not lying to me. It's a real simple conversion. If you're worried, bless you, if you're worried about it, let me know, and I'll show you how to do it, but I'm assuming that you can. It's just a unit conversion. Okay, now I'm looking for the angle. And what I do is I start with the transfer function. So here we go, there's the transfer function. Okay, let me just erase it. Here's the transfer function. Step 1, everywhere you have an S, you're going to replace it with I omega. Okay? Step 2, you're going to draw a picture of all the terms. Okay? 1, we're going to draw it over here. There it is, that's a 1. Draw a picture of this term. Okay, it's 10 to the right and omega up. So it comes over this way and up. So it's like that. This is 10 and this is omega f. Okay. Then you find the angle of each one of these vectors. The angle is measured from the positive real axis counterclockwise. What's the angle of that one? 0 degrees. So this guy right here is 0 degrees. What's the angle of the other one? You got to pull out your calculator, and it's the inverse tangent of omega f over 10. Boom, 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 right? Simple. Positive angle, right? Okay, so now you combine them. Everything in the top, you add. Magnitude, you multiply. Angle, you add. Why? There's theory. What? You don't want it, but you add. Okay, what's the angle of this guy? 0. Minus. Let's get all the guys in the denominator. There's only one. What's his angle? Oh, it's the inverse tangent. Omega f over 10. Okay? So you can punch it out. As the omega changes, the angle's going to change. Kind of makes sense, right? So if the omega is really, really small, what would this angle be? Omega f is real small.
0.
It'd be 0, right? Because this is small angle over 10, small inverse tangent. This is real small angle. Okay, so this guy ends up being 0. So the difference is 0. So basically, if you go slow enough, the output will follow you. When you peak, he peaks. When you trough, he troughs, right? Why? Because he's got plenty of time to keep up with you. He's got a time constant, but it's okay, right? It won't be ever 0, because if this is anything other than 0, there will be a small angle, right? And it's a negative, isn't it? So he'll be behind you a little bit, right? He's not anticipating where you're going to be. He follows you, right? So his angle will be a little bit behind you. Okay, what if he ends up so far behind he's over 180? Well, then we say he's leading. But he's always behind you. But it looks like he's in front of you, right? Because he's so far back there. It's like he peaks and then you peak. He troughs and then you trough. Well, no, his trough was from your previous trough, right? But he's so far behind you, it just looks funny. And so then it looks like he's ahead of you. Okay, so we'll say he's leading. Okay, so far behind, it looks like he's leading you. But they never lead. They can't anticipate what you're going to do. They just respond to you. Okay? Because the theory says everything on the top is added, everything on the bottom is subtracted. Stop by the office and I'll prove it to you. But it happens. I mean, you know, the thing about theory, the way I always saw theory, it's like, okay, thank you very much. It works. Why didn't you just tell me that? Why do I need all that theory? Well, if you're a PhD and you're writing, you know, journal papers, or you're trying to find a new way, a better way to do something, the theory is important. If you're just going to be a practicing engineer, you use the tools that somebody developed for you, so use the tools. So if you go to graduate school, stop by and give you the theory, okay? Because then you're going to have a different kind of job, right? You need to build better tools, not just use them. Does that make sense? So my philosophy is, undergraduate, I'm going to teach you tools so you can make money, right? And share it with me. Right? That's going to happen. Okay, so now you can find the angle, you can find the amplitude, the magnitude, right? Feel comfortable with that? Now let's just practice it. How about a second order system? You want to do second order? Yeah, we do. Okay, all right, man. I love that enthusiasm. Fantastic. Okay, let's do a second order system. Okay, second order system. Let me see if I can blow this thing up. Is that big enough or bigger? Bigger? That's unstable. All right, is that big enough? Okay, so now what I'm going to do is I want to solve this. What's the order of this guy? Second order. Who's the output variable? X. I could have put a constant in here, but I'm just cutting to the chase, right? You know how to handle constants. You know all that stuff. Let's just look for the sinusoid. What do you think is going to happen when you do this? Will it have a tendency to oscillate?
Yeah.
How do you know? How do you know?
Omega.
Very good. Very good. Remember that second order form? Second order form. Is this a second order? Yeah? Is it in the second order form?
Yes.
Yeah, because there's a 1 in front of there, right? What's the omega n? What's the natural frequency?
1.
Square root of 1? Right? Square root of 1? 1. Okay, what's the zeta? The z?
1/10.
Yeah, 2z times 1 equals 1/10. 2z times 1 equals 1/10, right? So z equals 1/20. Does it oscillate with a z less than 1?
Yes.
Yes, anything with a z less than 1, it will have a tendency to want to oscillate. Okay, what's the natural frequency? 1 radian per second. So if this were an exam, you nail it, right? I said, what's the damping? It's 1/20. Everybody okay with that? It's called underdamped. I think I said that before. It's underdamped, right? Okay, so it does have a tendency to want to oscillate. What's going to happen when I shake it?
Keep shaking.
It's going to oscillate, right? What frequency? This is a 1. What frequency? If I put in a 10 right here, what frequency is it going to oscillate at? The 1 or the 10? Huh? With the 10, yeah. Okay, so let's do this. Here's the solution right here. Here's the solution right here. What the heck is going on here? What's all this garbage here? The transient. Very good. This is the transient. Why is it lasting so long? Because you got a small zeta. You got a small zeta. What's the time constant? You remember what the time constant in terms of zeta and omega is?
1 over zeta omega.
1 over zeta omega. Zeta is real small. 1/20th. Is that what we said? 1/20th. The omega is 1. 1 over 1/20th times that's 20. There's 20 seconds is the time constant. It's going to take 80 seconds until it finally gets to where it's going. Does that kind of look like it kind of makes sense? Yeah, so right around in here somewhere, it's finally saying, okay, I'm through with the transient. Now let me just kind of settle into what I'm going to do. You see that? So graphically, when you're doing experiments, you'll see this kind of junk and you're going, man, this is not a frequency of 1. Look at this. This is not a frequency of 1. And it's certainly not a frequency, I forget what I put in there, 10 I think or something. What did I put in there? 1/10. It's neither one of the, it's weird. Well, it's a transient. It's a mixture of the two. right? And he, bless you, and then eventually, about 4 time constants, bam, it finally said, that's all gone, and now I'm down to the steady state. Notice the steady state is not constant, right? So what's the amplitude here? Is it this? No. You wait till you get to steady state and say, what's the amplitude when you get to steady state? Got it? Okay. What would happen if you increase the frequency? What happens if the frequency, this forcing frequency, is well below the time constant? What would you expect to have happen? It would settle in and it would follow it. The amplitude of the output would be pretty close to the input, and there would be very little phase shift. Does that make sense? Because it's got plenty of time to keep up with you. What would happen if it's really, really fast? The forcing is real fast compared to the time constant.
Small amplitude?
A small amplitude, because by the time it knows, you know, it can't make it there, and then it, right? Same thing. Same thing. You got a good head on your shoulders. You know how these things work. All I'm trying to do is say, okay, let's put some math to it. That's it. How would you think you calculate the amplitude if this were on a test? I want the amplitude of the steady state solution. Use the transfer function. Man, somebody's learning. All right, so let's start with, I'll look over here and I'll go back to the differential equation. We'll write the transfer function. All right, so the differential equation was x double dot plus 1/10 x dot plus 1x equals f times the sine of omega t. Okay, so this right here is my input. I better call it, I'll call it Q. That's my input. Bless you. Okay, that's my input. What's the transfer function?
Laplace transform.
Very good, and it's output over input. I'm going to get it like this. I don't want to waste time, right? So see if you can do this. It's going to be output over input. I'll use capital letters to say that I did a Laplace transform, and this guy is going to be 1 over s squared plus 1/10 s plus 1. See how I did that? Now you can put in as many steps as you want, but this is where you want to go and start. You don't get any credit on the exam until you do more than this, right? So you want to get there quick. Everybody okay with it?
Right. So with so the Laplace transform was s squared x s x.
Yep, 1/10 s x.
And then what is it just for x? Just 1?
Just x. Yeah, 1 times x.
Okay.
So it's like taking a derivative, except instead of dots, it becomes an s, right? And then you have all that other junk, the initial conditions. We ignore that. Okay, and then if you notice, you take kind of a cross multiply or whatever. Everybody okay with that? Okay, good. Now, what do? Yeah, if it was a constant that I wanted the steady state of, I would put, you know, those 4 steps. That's not what I'm doing. I'm doing sinusoid. So everywhere you have an s, you're going to plug in I omega. Okay, so this is going to be 1 over I omega quantity squared plus 1/10 I omega. This would be the force of the omega. Plus 1. Oh, by the way, let me just make sure. I think you do know this, but how would you, if you had this, how would you find the time constant?
Set that equal to 0.
Yeah, so you set this equal to 0, and you solve for your s's. Let me ask Mathematica because I don't remember the quadratic formula. If you all do, shout out the answer. Okay, so I'm going to say solve s squared plus s divided by 10 plus 1 equals 0. Solve it for s, bang, and show it to me as a number, boom, And it says that the two S's are minus 0.5. S equals minus 0.5 plus 0.998 I and negative 0.5 minus 0.998. Okay. Is it stable? Why not? Not the imaginary, right? What you're looking for is, if I say stable, you look for the real part. Write this in your notes. If I say stable, you're looking for the real part of the S. Here's the real part of the S. Is it negative? Okay, then you get an e to the negative something t, it's stable. Okay? The fact that it's imaginary, all it means is I want to oscillate. I want to oscillate. That's all it means. What's the frequency of oscillation? 0.998. Might as well be 1. Get the idea? Okay. What students will do is they'll say it's unstable. They'll look at this one here and say there's a positive guy right there. It's unstable. No, you'll always get them in pairs. They will always come in pairs because it's always the quadratic formula, and they always come as plus or minuses. They always come in pairs. Don't look at this and say it's unstable. It's nothing to do with stability. It's only the real part.
So it wants to oscillate with a frequency of 0.998.
Yep.
That's radians per second?
Yes. Radians per second. What's the time constant?
Half a second.
It's negative 1 over this. If I were to ask you, draw me a root plot, you remember the root plots? You plot the S's on the real and imaginary. So you do this. Here's the real part, here's the imaginary part. Where does this lie? Left and up, right? Let's call that 1. Is that close enough? So the left is 1/2 1. So it's right here and up 1/2 1. So right about there. That's this guy. Where does this guy lie? Over and down, right? So he'd be right there. They always come in pairs. They'll always be symmetrical around here. Always, always, always. They have to be, because it's always a square root that, quadratic formula will create them. From this root plot, can you tell me what the time constant is? You got it from zeta and omega. Very good. Put it in standard form. What it is it's 1 over this horizontal distance. 1 over that distance. So on the test, if I draw you a root plot, you can give me the time constant. Yes?
Say that again.
Okay. The time constant is the real part. 1 over the real part. The real part is this horizontal distance. 1 over that distance. That's your time constant. I'm not telling you it's any different, right? You take 1 over this. Negative 1 over this, right? That's the real part. 1 over that. So if I draw you a plot, you can say, well, I'll find that distance. Boom, 1 over that. Is it negative 1 over? What's your time constant here? Right? You remember how officially it's e to the some power t, right? And the way you find the time constant is you take this, set it equal to a negative 1. Your e is going to be e to the minus 0.5 t. So you take this, set it equal to minus 1, so it becomes a positive number. So to memorize it, you take this, change the sign, invert it. To memorize it, you take the horizontal distance, invert it. What if I give you a root plot like this? What do you tell me about that? Stable or unstable? Unstable. The real part is over in the positive part. That's unstable. I said, what's the time constant? You say, it ain't no time constant, never gets there. Doesn't disappear. There's no time constant on an unstable system. It blows up. Never gets to steady state. You see that? So you can do it with the root plot, you can do it with the S's. It's all the same. Depends on what you're given. Okay, back to where we were. Okay, so that you found the time constant, found all those things off the... Okay, how about this one? What do you do with this? You draw a picture of them. Okay, so...
Just to be sure the time constant was 2, right?
Time constant is 1 over 1/2. 2. You're thinking to yourself, why can't you just answer? Okay, I'm going to get the easy one. I'm going to draw a picture of that guy. You don't have to draw the picture when you get good at it. Boom, there's the one. Okay, y'all do the next one. Is there an I squared axis? You see an I squared axis over here? No? So you better get rid of that I squared. What's I squared? Okay, let's just kind of simplify this. I'm just going to look at the bottom one. What's an I squared equal to?
-1.
-1. Do y'all realize that? I squared is a -1? Okay. I is the square root of -1. So if you square that, it's -1. Square root of a -1 times square root of a -1, it's equal to a -1. What's I cubed?
Negative I.
Negative I. What's I to the 4th?
1.
Right? Because it's I to the 4th is I squared squared. -1 squared, 1. This guy is I times I squared. I squared is -1 times I. Right? Okay, so this would be a -1 omega f squared plus omega f over 10 times I plus 1. Okay, draw a picture of that. What's the real part? Not quite. Is this real? Yeah, it is. You see an I? I don't see an I. So it's a 1 minus that, right? So it's 1 minus omega f squared plus omega f over 10 I. Isn't that the real part? And that's the imaginary part, right? So this guy is over here. How big is he? He is 1 minus omega f squared. And his vertical is omega f over 10. How big is he? That guy squared plus that guy square root, right? So the magnitude is, okay, so the magnitude, the guy on the top, how big is the guy on the top? Let's draw him in the picture over there. How big is he? 1. Okay, so it's 1 divided by, okay, the bottom guy. How big is that? I drew a picture of him. How big is he? Square root of the real part squared real part squared plus the imaginary part. Is that right? Okay. So what I can do is ask Mathematica to plot that for me. Or you can do it in Excel, it makes no difference. I'll just put in different omega f's and I'll plot the magnitude. Is that good? Okay, I did that. And this is what I get. Go, okay, I'm going to pull this down. There you go. Does that look like what you expected? No. What the? Over here, the magnitude is 1. Is that kind of what you expected? At low frequencies, the amplitude is the same, right? Because he's following you, right? At really high frequencies, what's it doing? I mean, if I continue it out, it will keep going. It's going to keep going down lower and lower and lower and lower. That makes sense, right? Because you're going so fast, he can't keep up with you. What the heck is going on in the middle? What in the world? This is the forcing frequency. Notice, you know, where is this peak occurring? Somewhere around 1, isn't it? What's the natural frequency? Isn't it somewhere around 1? What's happening is you're forcing it near where it likes to oscillate. And it goes nuts, man. Just like I told you, you take a drunk and man, it's easy to get them to get drunk, right? You take something that wants to oscillate, you say, okay, I'm going to wiggle you at that frequency. Man, it says, hey, I love it. That's what I want to do anyway. Let me give you an example. How many of you have pushed a loved one on the seat, on a swing? Right? You gently push them, they come back, you wait for them to come back, you gently push them, don't you? Now, if you're at the end of your relationship, maybe you go, right? You gently push them. They have a natural frequency, they come back. You wait for the natural frequency, and then you excite them again at that natural frequency. And you don't have to push them hard. And before long, man, they are going like nuts and screaming and hollering, okay, I'll do anything you want, let me on the swing, right? Isn't that how you get them to swing? What would happen if they're stationary, you grab the swing, and you do this to them? Are they going to go very high? They'll probably slap the crap out of you. Do they go very high? What's happening is you're forcing them at a frequency they don't want to oscillate at. They don't want to swing at that frequency. And so the amplitude will not be very, will you have an amplitude? Yes. Depends on how heavy the person is, how much muscle you got. But yeah, you can force them to go in and out, right? You can force them to. But that's not what they want to do, and they will not give you a very large amplitude. That's what's happening here. If it's real fast. Now, if it's real slow, right? Like on my kids, they're lightweight. You can grab them like this, and you can push them really slowly and hold on to them the whole time. That freaks them out too, right? Can't you? I'm sure you've done it, right? You push them, and you can hold them there, and then you say, okay, and then you're going to come back, and you're going to hold them there, right? You can force them to do what you're doing, right? The swing will go with you. It doesn't fall out of your hands. You with me? If you do it slow enough, what does that mean? Below the natural frequency, right? Below the time constant, okay? Do it below just like first order. They go with you, right? But if you really want the excitement, what you're going to do is you're going to push them at that natural frequency. You wait till they come back and you push them again. Now, if you look at the energy and you say, how much energy am I putting into this? If you oscillate them at a low frequency, like pushing the swing up and holding it, bringing it down and holding it, you're not putting energy in. What you're going to do is you're going to put a little in, right? They've got some good potential energy. Then you're going to take it back out and lift them up here, and now they've got some energy. Now you're going to take it back out, right? So you're not really contributing energy to them. You're just, putting it in, taking it out. If you're at the natural frequency and you excite them there, you're putting energy in, right? So you gently tap them. How much work did you do? Hardly anything. Because you just tap them. Small force, small motion. Small amount of energy. They gather that, they go up and they come back. Then you tap them gently again, a little further, tap them gently again. How much work are you doing? Not much. Every cycle you put a little bitty tiny amount of energy in, and before long they're going like this. Where did that energy go? It's in the swing. So here's the deal. You want to put energy in something. Maybe you want to make a bomb, I don't know. Or you want to shake cans of paint at Home Depot. Right? What do you want to do? You want to get the energy in the paint, right? So where are you going to shake it? At the natural frequency. Okay? When you shake it at the natural frequency, though, you got to be aware, what is the amplitude going to do? It goes crazy. So if you get right on that natural frequency, man, it goes nuts. And it will be shaking like crazy. And all of a sudden, if you're not careful, you're going to break something. Because it's bending, and all of a sudden it breaks off and there goes your paint. Make sense? You see how that works? Okay. So that's what's different about a second order system. But we do it the same way each time. This is called a resonance. And it's a real problem when if you've got a pump, for example. If you happen to run the pump at the natural frequency, the pump will start shaking like crazy. Same thing happens with ceiling fans and all that. But if you're excited at the natural frequency, it goes nuts. Okay, we'll finish this up and I'll move forward. But I think you have a good feeling for what transfer function is, what it's good for, amplitude, and turn in so I know who is on what team. And if you need help finding a team, hang around and I'll help you find a team. All joking aside, you're not an idiot, you need help.